Okay, so now let's turn our attention to the energy of an ideal gas. Well, standard textbooks start their treatment of the subject with a study of the collisions of the ideal gas particles with the walls of the container. Now, ideal gas particles are point masses which, because they have no size, never collide and move in straight lines between collisions with the container, which we suppose to be spherical with radius a. It assumed that energy is conserved in the collisions with the container so that the particles move with constant speed in straight lines. In the paper we show that if the walls of the container are modelled by an elastic solid, energy can be transferred from the enclosed gas and the surroundings through collisions with the wall. However, if the collisions are perfectly elastic, the speed of all the particles will stay constant so that any initial distribution of speeds will not change. If we put the origin of coordinates at the center of the sphere, then the coordinates of a particle which has just collided with the wall can be established using this formula. So this is a vector with radius a and described by two angular variables, theta, which corresponds to latitude, is called the polar angle, and phi, called the azimuthal angle, is analogous to the latitude on the Earth. We can check that that is a vector on the surface of the sphere by calculating the square of, or the scalar product of the vector with itself, using this to see that the result is a squared. So that means the length of that vector is always a. And now we can define the velocity of the particle in general using these coordinates, u, v and w, and then the parametric vector equation of the trajectory of the particle we can write as the initial vector plus t, which is a parameter and is actually time, times the velocity vector. So let's do that and think a bit. And we can see that this vector, or this vector r, is a linear combination of the radius vector from the origin and the velocity vector, so it lies in the plane determined by those two vectors, or spanned by those two vectors. Well, when the particle collides with the wall, its distance from the centre will again be a, so the left-hand side of a quadratic equation for the time of the next collision with the wall can be derived using this. And we can see that this is a quadratic equation for t, so we take the scalar product of the parametric vector with itself and subtract off the radius, and we get this quadratic equation, and we know Mathematica knows how to do that, so we solve the quadratic equation and we get 2 times. And t equals 0 is obviously where the particle starts, and this value here could be, depending on the parameters, either positive or negative. Well, if it's negative, that means that the particle that we're looking at the collision, the previous collision, and if it's positive, then we're looking at the next collision. And that is, this thing here is proportional to the cosine of the angle between the velocity and the position. So anyway, so let's go on. And now we can insert this time, the second one of course, into the expression for the position vector to find the position of the next collision, which is this kind of horrible looking thing. And now when the particle collides with the wall, its normal component of velocity will be reversed. Well, what's the normal component of the velocity? Well, it's the scalar product of the initial velocity with the radius vector, and then times the position vector, and then divided by the square of the length of the position vector. So we get this, and this is therefore a unit vector perpendicular to the sphere at the point of collision. And now to get the new vector, this component of velocity is reversed, so we subtract off twice from the velocity vector, and that will give us the velocity after the collision. And now we want to see that this is in the plane spanned by the initial position and velocity. Why do we want to do that? Well, let's see. We take the scalar product of the vector product, sorry, of the initial position with the velocity, which will be a vector perpendicular to the plane of the initial motion, and then we take the scalar product of that with the new velocity vector and see what it is. Well, 0, and that means that the new velocity is perpendicular to a vector perpendicular to the original plane of motion, so therefore the new velocity is also in the same plane. So this means that the trajectories before and after collision lie in the same plane. And this must hold for all subsequent positions whose collisions, whose positions thus lie on a circle. And now we start there and we do another collision. So we take the parametric equation of the trajectory after the collision is given by the position of the collision plus t times the velocity vector. So we calculate that, and that looks pretty horrible, but doesn't matter. And now we can find an equation for the time to the next collision using that. And this looks rather like the same one we had before, and let's just check that. So this was the previous equation, and we can see that they're identical, and therefore that the time to the next collision or the second collision is the same as the time to the first collision, and so on and so on, so that the time between all the collisions is a constant. So now let's see if we can visualize that. So we need to take some values. So we take the radius of the sphere to be 1 and the initial azimuthal angle to be minus 2 pi over 5, and the initial, did I say azimuthal? This is the polar angle and this is the azimuthal angle. And we take all three velocity components to be 1. So these are assignments which set numerical values of the parameters. And so let's work out where the initial position of the particle actually is, and it's there. So we can put that into a file of the collision points. So let's do that. So we initialize that file of coordinates using that, and then as we calculate new ones, we'll append those to that file. And now we calculate the initial velocity numerically, and it's of course that.